This is an introduction to graph theory and using Mathematica to study graph theory. First, let's define a graph. A graph is a set of vertices or points and edges or lines connecting those vertices. Here our vertices are Jim, Sam, Abby, Tom, and Corey, and the edges are the lines connecting them. So the vertices are people in our example, and the edges could represent a number of things. In our case, we'll say that edges represent friendship. That is, there's a friendship between two people if there's an edge between them. And if there is no edge, then there is no friendship. So Jim and Sam are friends, and Jim and Abby are friends because there are edges between them, but Jim and Corey are not friends because there's no edge between them. Our edge set, or first our vertex set, consists of Jim, Sam, Abby, Tom, and Corey, and our edge set is the set of relationships, Jim and Sam, Jim and Abby, Sam and Abby, and so on. Now you may wonder what this has to do with linear algebra, and it turns out all of this information can be encoded in a matrix, and we call this matrix an adjacency matrix. We label all of the rows and columns of the matrix with the names of the vertices. So here Jim, Sam, Abby, Tom, and Corey goes along the rows and the columns. We're going to populate this matrix with zeros and ones with the following rule. 0 means that there is no edge. And if we put a 1, that means that there is an edge between two vertices. By convention, we say that no one is connected to themselves, so Jim is not connected to Jim. There's no loop going from Jim back to Jim, so we put a 0 in this first spot. However, Jim and Sam do have an edge going between them, so we put a 1 there. And the same for Jim and Abby. There's an edge there, so we put a 1. Jim and Tom do not share an edge, so we put a 0. And Jim and Corey don't share an edge, so we put a 0 there as well. Now we jump to the next row, the row for Sam. We already saw that Sam and Jim are friends. There's a 1 there, so we put a 1 there. Sam is not friends with himself. There's no loop going from Sam to Sam, so we put a 0 on the diagonal. And Sam and Abby share an edge, so we put a 1 there. Sam and Tom have an edge between them, so we put a 1 there. And Sam and Corey don't have an edge between them, so we put a 0 in that position. Now we jump to Abby's row. Abby and Jim do share an edge as we saw before, so we put a 1 there. And Abby and Sam share an edge, so we put a 1 there. Abby is not connected to Abby, so we put a 0 on the diagonal. And Abby and Tom are connected, but Abby and Corey are not. And we go through the rest of the rows, filling in the entries following our rule for when we put 0s and when we put 1s. So this is the resulting adjacency matrix for our graph. It turns out that we can put this information into Mathematica, and Mathematica can help us in doing some of the computations that we may want to do with this information. To define a graph in Mathematica, we use the graph command. First, I'll set it equal to a variable g just so that I can refer to it in the future. We just type graph with the bracket, the square bracket, and then we put our edge list in curly braces. So first we want to say that Jim and Sam are on an edge. They share an edge, so we put Jim in quotes, that's the name of our vertex, and then we define the edge between them in the following way. We use the left angle bracket dash right angle bracket to define an edge. And then we put Sam in quotes as well. We separate each edge by a comma. And we saw that Jim and Abby were also on an edge. So again, to define the edge, we say Jim in quotes and then left angle bracket dash right angle bracket. And then we put Abby's name in quotes. Now I've already done the rest, so I'll just grab those and paste them in. Then we close the curly braces, close the square brackets, and if we run this, we get the following graph, which looks a little bit different than we saw before. So this is the same information, even though it looks a little bit different. Instead of being in a circle, the points are arranged differently. it turns out that I can arrange those points in a circle so that they look more familiar by changing the graph layout. And here I'll choose the circular embedding to put them in a circle, and when I run this, it looks more familiar. At a glance though, I can't tell which vertex is which, so I can turn on vertex labeling by typing vertex labels and then selecting name, and that means that it'll give the name of each vertex above each vertex point. So if I run this, I can see at a glance which one is which. So this one is Corey, this one is Tom, and so on. Now Mathematica can also be used to find the adjacency matrix of this graph. So I can set that equal to a variable just so I can refer to it in the future. And I type adjacency matrix of the graph G that we just defined. Now if I run this, it's not going to give me a matrix of zeros and ones as I might expect. Instead, it's going to give what's called a sparse array. A sparse array is the most efficient way that Mathematica can store a large number of zeros and ones. So that's why it returns the sparse array rather than a matrix, which would be more system intensive. Here it gives us a little diagram of what the adjacency matrix looks like. These zeros are the dark blue and the ones are the light blue. I can force it to give me the matrix form, and if I do that, it gives these zeros and ones as we're used to. Now notice that the matrix form can't be used in any further computations because matrix form essentially stores the matrix as a picture rather than as a list of numbers. And so when we try to do computations, we can't use the matrix form, it'll do it symbolically rather than using the individual entries of the matrix to do the computation. So we'll take that off and just work with the sparse array. Now we can go back to our document to look at some other properties of the graph. First though, let's do some relabeling. So we're going to relabel the vertices of the graph as places, so place 1 through place 5, instead of people. And that's because I can think about distance between places more naturally than the distance between people. So the adjacency matrix encodes some other information. It also encodes the number of paths between any two vertices of length 1. So I see if I want to go from place 1 to place 2, I can go along this edge. That's length 1, and that's this one here or this one here. So notice that I can't go from place 1 back to place 1 with a path of length 1, so that's the 0 in this first position. So this encodes the number of paths of length 1 between any two vertices. Well, what if we want to compute the number of paths of a larger length between vertices? It turns out that if we square the adjacency matrix, we get the number of paths of length 2 between vertices. So let's look at how that happens. This is the square of the adjacency matrix, and if I look at this 2 right here, that's telling us that we can get from place 1 back to place 1 using a path of length 2, and I can do it in 2 different ways. So I could go down this edge and then back up that same edge, or I could go down this edge to place 3 and back to place 1. So those are the 2 different ways of going from place 1 back to place 1 using a path of length 2. Maybe though we want to look at the number of paths between some other vertices. So let's look at the number of paths of length 2 between places 1 and 4. So in our adjacency matrix, or the square of the adjacency matrix, we see that there are two ways to do this as well. I could first go from place 1, make a pit stop in place 2, and then continue on to place 4. That's one way to do it. But I see another way to do it as well. I could go first to place 3 from place 1, and then on to place 4, and that's the second way of getting from place 1 to place 4 with a path of length 2. And as we can see, these are the only two ways to do this. This generalizes, so I can look at the number of paths of length 3 between vertices by looking at the cube of the adjacency matrix. And in general, the kth power of the adjacency matrix, or a to the k, gives the number of paths of length k between vertices. Now, if we want to do higher powers, we can quickly see that this is not going to be very scalable for doing it out by hand. So we're going to look to technology to do this. So here's where we go back to Mathematica to compute the number of paths of larger lengths between vertices. So here, to be consistent, I'll relabel these vertices with the numbers 1 through 5, and this is exactly the same as it was on the previous page. So this is just place 1 is the number 1, place 2 is the number 2, and so on. So here we have a new graph that is the same, just different labels for the vertices. The adjacency matrix is also the same. And now we can look at computing the powers of a matrix. So we can do that a couple of ways. We could either look at a times a, so that'll give us a squared. If I throw that into matrix form, that's the matrix that we saw previously. Now, this might be tedious if we're trying to look at the 17th power of a, because we'd have to multiply a by itself many, many times. Instead, what we can do is use the command matrix power. And we want the matrix power of a, we give it the matrix, and we want, say, the second one. And let's put it back into matrix form just so we can verify that it's the same matrix. So this is another way of computing the power of a matrix. Notice that if you raise it to a caret like this, so we put a to the 2, that's going to give us all 1s and 0s because Mathematica goes through and it squares all of the entries individually rather than the matrix. And that's not what we want. So we are going to use matrix power to give us the correct power of the matrix. Now maybe we want to look at the number of paths of length 17 between two vertices. So to do that, we would run this matrix, and this is going to give us some bigger numbers. And we can see right away that we don't want to do this out by hand. So this says that if we look at the number of paths of length 17 between places 1 and 3, there are 3.2 million ways to do that. These two entries tell us the same thing. So the first row and the third column and the third row and the first column contain basically the same information. This has been an introduction to graph theory, but we'll use Mathematica to learn more about graphs in the future and use the linear algebra to learn more about graphs and the systems that they model.